Hello and welcome again to YCP Chemistry Labs, York College of Pennsylvania's YouTube channel to get you ready for lab each and every week. This week we're discussing the Aspirin Part 2 Qualitative Analysis Experiment. This experiment obviously follows up on what we did last week when we created a sample of acetyl salicylic acid, or aspirin, beginning with salicylic acid. So today we want to begin to investigate our sample, or rather samples if you recall, from last week. Because when we left the lab last time, you should have had two samples. The raw stuff that you made, which might have been a little clumpy and sticky looking, and then a recrystallized version of your aspirin. So you took some of that raw aspirin and you dissolved it into ethanol, and then you slowly allowed the crystals to reform, with the intent being to hopefully improve the quality of the sample. So today we're really trying to perform a before and after comparison, if you would, or even a before, after, and after, because we have two stages of after. The after the reaction, which leads to the raw sample, and the after the recrystallization, which hopefully will lead to the purest sample. So there are lots of ways that scientists and chemists have to study the quality of a sample. Many chemists employed in industry, in fact, are in quality control, where they're gauging the quality of a product before it can be sent to market and used by consumers like us. So we're getting a taste of that in this week's lab, trying to decide if we successfully did make aspirin, and then trying to decide how well we did that job. What is the quality of our sample? So we're going to use three different forms of analysis today. And these are all called qualitative because they're not going to give us any numerical data necessarily to look at, but we're really going to have to put our skills of observation to the test in this lab today. All right. This harkens back to a lot of early chemistry, which is what we often call descriptive chemistry, taking very good notes, being very detail-oriented about comparing two different samples. And that's actually where you'll start your lab today. You will collect your samples from last lab period, which should be nice and dry by now, and you want to make some notes about how they look. Colors, size of the crystals, maybe shapes of the crystals, clumpiness versus being dry. Are the shapes of the crystals needles, or are they more cubic in shape? Any adjectives that you can think of to describe the crystals and the products would be great to help you convey if they look different as what you believe is aspirin versus the salicylic acid that you started with. So you really need to do that same thing about gathering details and descriptions for the salicylic acid as you do for your aspirin samples, raw and recrystallized. Then you'll engage in a series of three different tests on your aspirin samples, salicylic acid, and store-bought aspirin. The store-bought aspirin is sort of a control to see how our sample compares to what you might be able to buy in the store. And the salicylic acid is being tested, again, to show that before and after. Is what you're looking at and believing to be aspirin different than what you started with last week, the salicylic acid? So the first test, although you don't have to do them in any particular order, but the first test we'll talk about is melting points, which we've already done this semester. We understand that a narrow melting point equals a pure sample. So if you were to measure the sample, the melting point range of your samples, and they come out to be very small ranges of only a couple of degrees, that supports the claim that you have a pure substance in the tube. On the other hand, if you get a wider range of maybe 5 degrees or so, then there's some impurity, or the other way of thinking about that is that it's a mixture. Perhaps the most common impurity that we're likely to have in our aspirin samples that we made is leftover salicylic acid that didn't react, all right, and is still there. That would mean you have a mixture in your melting point tube, and so you might expect a larger melting point range. So I would expect that the raw sample, which is more likely to have any contaminants in it, would probably have a larger melting point range, which also, remember, means it should be lower as well. Mixtures have lower, wider melting points than pure compounds. And I would hope that our recrystallized sample has a narrow melting point range which closely matches that of aspirin, pure aspirin. Now, melting points are also things that you can look up. And indeed, that's one of your pre-lab questions, to look up what are the melting points of salicylic acid and aspirin, acetylsalicylic aspirin. You want those two as an idea of comparison, I should say, for where your experimental samples are coming in against. All right? If they come in close to the acetylsalicylic pure melting point, but maybe are a little wider, you've got good evidence that you did in fact make acetylsalicylic acid during last week's experiment. Okay? So pure compound would be narrow, wide would be impure. So you're going to need to do several different melting points of your raw, of your recrystallized. You can do melting point of your salicylic acid and of the store-bought, just to see how everything compares. Another interesting test that we can perform is the formation of a complex with iron ions. Iron 3 ions will react with salicylic acid. They form a complex, a grouping, in other words, that turns a deep purple in color. Aspirin cannot complete this same reaction. In other words, I can't put aspirin here in place of salicylic acid and get the purple compound. So you'll first sort of prove this to yourself by putting some salicylic acid into the iron solution, and you'll see the intense purple color. Similar to the crystal violet color that we saw earlier this semester, but it's not the same chemical at all, just coincidentally it's a purple color. And then, if you try that same experiment with the store-bought aspirin, you would see that you don't get the purple color. The solution remains its orange in color because that's the color of the iron in solution. So when you try your samples of aspirin, your raw and your recrystallized, if any purple color develops when you add it to the iron solution, that's an indication that salicylic acid is present, because only salicylic acid will form the complex with the iron. All right? If no color change occurred, that's good qualitative evidence that your sample does not contain salicylic acid. Careful here, it's not saying the sample is pure, it's just saying the sample doesn't contain salicylic acid. All right? There's a limit to what we can conclude from our qualitative tests. All right? And so you'll test 4 things: pure salicylic acid, pure store-bought aspirin, your raw sample of aspirin, and your recrystallized sample of aspirin. Now, because these all might have different colors and you want to write down good descriptions of them, another good idea to capture that data might be to take a picture. If you have a camera, a cell phone camera handy, it might be good to line up your 4 test tubes right next to each other with a nice white, bright background that would show the difference in the colors, and then take a picture so that you can remember it. You obviously want to write good notes to yourself in the lab as well, but a picture could be very helpful, and you could include that in your lab report perhaps when you go to write your final lab report in a couple of weeks. Okay? The last experimental test that we're going to perform on our samples is known as thin layer chromatography. All right? In a second, I'll get the board erased and I'll tell you a little bit more about TLC. Okay, so I've got it set up here now to describe this last qualitative test that we're going to perform on our aspirin samples this week. It's called thin layer chromatography. Thin layer chromatography takes advantage of the different polarities that molecules have. Polarity is, of course, a topic that we addressed earlier this semester when we looked at intermolecular forces, and it's a result of the shape of a molecule and the types of bonds that are present and the electronegativity differences of all the different atoms that are in a molecule. Long story short, our two different compounds that we're really interested in this lab, aspirin and salicylic acid, have different polarities, and they should behave slightly differently then. And thin layer chromatography is the test that should distinguish them from one another based on the polarity differences. So in thin layer chromatography, or TLC, you have a plate. Now I've drawn a giant sized one. In reality, your plate will be smaller than the size of this marker that I have in my hands right now. And it will be as thin as a sheet of paper, essentially. All right? We call it chromatography paper for that purpose, all right? For that reason. But I've blown it up here to demonstrate what we're doing. So usually we run a comparison side by side of different chemicals that we're interested in. So on our TLC plate, we have 4 chemicals of interest today. We have pure salicylic acid. We have store-bought aspirin, again as our control for comparison. We have the raw aspirin that we made, and then the recrystallized form of our aspirin. When we put those on the plate, and I'll describe that next, and we run the TLC plate with solvent or eluent, what happens is it's like a wave coming in from the ocean. If you've ever been on the shore and had waves come in, you feel them pushing you back in towards the beach. But if you really dig your feet into the sand, you can perhaps resist those waves as they come by you. And so the more dug in you are to the sand, the less you get moved. So now in the chemistry analogy here, chemicals that really are attracted to the chemical on the surface of the TLC plate are like people who really dig into the sand when that wave comes in. But other people who don't really care at the beach about getting pushed by the wave, or maybe they want to have that feeling, they don't dig into the sand, so as the wave comes in, they get pushed inshore. So our, quote, wave is our solvent that will soak upwards along the plate. It will be drawn up the plate by its attraction to the chemicals on the plate. So a chemical has a choice then to make. Do I like the material on the plate and I want to stay where I'm at, or do I like the liquid that's moving up the plate and I want to move with it? All right, just like staying in place on the beach, or allowing yourself to be pushed inland with the ocean, okay, with the wave. All right. So how do we get the chemicals on this plate here? All right, we're going to dissolve small amounts of the chemicals into alcohol or our eluate mixture, okay, and then we use a very thin straw. It looks a lot like the melting point tubes that we've used this semester, but it's open at both ends. So it literally is a straw, but a very, very narrow straw. When you touch that straw to the liquid in the plate, some of that liquid will be drawn up into the tube itself. I'm using green there to show that color. All right, it'll draw about 1/3 or 1/2 of the way up the tube. So you now have a sample of your chemical. You bring that over to your plate, and you've pre-marked your plate with a starting line. That's very important. And with a couple of little marks, so you have a spot to aim for. And then very carefully you want to touch, ever so briefly, you just want to touch the tube onto the plate, and it will leave a little droplet around where the tube was. You don't want all of the liquid to drain out at once. You just want to tap it and get a very narrow dot. Because what you're going to need is 4 dots side by side that do not overlap with each other. Okay? So instead of just thinking about one person at the beach, now imagine you're there with 3 or 4 friends. But we don't want you hanging on to each other. We want to see who is going to be the best at digging themselves into the sand and resisting the wave as it comes in. So we can't have our spots touching each other. They need to be distinct. And so that's best done by quickly tapping the tube onto the plate, letting that spot dry, and then tapping it a second and third time, right on top of the original first spot. Okay? Once you have put your spots on your tube, they're going to be invisible to the naked eye because all of our chemicals are white in color and they're dissolved in solution. But we can visualize them with ultraviolet light. So I recommend you take your plate to the ultraviolet lamp that's available in lab and look at it under the UV lamp. And the plate will glow green and your chemicals will not glow. They will have like a shadow, or they might glow purplish in color underneath the UV light. And so then you should be able to see your 4 spots, or if you do it one at a time, maybe you'll see each spot as you add it onto the plate. Okay? So that's how we prepare our plate so that we have our 4 distinct spots on here. And they're all starting at the same place as we're going to allow then solvent to run up the plate. We do that in a beaker. Pretty simple. You're going to prepare a beaker so that you can lay the plate against the edge of the beaker. Okay. You're going to add some solvent, or as we call it, eluent, for this experiment to the bottom. It's very important that your starting line on your TLC plate be above the eluent. We want you above the waves, in other words, before the waves start coming in at the beach. We wouldn't want you already in the ocean water. That's, again, using that analogy here. So you want your chemicals, because they're on the starting line, they need to be up above the liquid level in there. Now, to help the experiment go a little bit faster, we use what we call a wick. It's half a sheet of filter paper. So just get a large circle of filter paper, fold it and tear it in half, and put 1/2, that semicircle, in here. The solvent will very quickly soak into the wick and saturate the airspace up here, meaning that the solvent should not evaporate off of our plate as it runs up the plate. Okay? This just makes the experiment go a little bit faster. Okay? So you put your eluent in, you add your wick, then you add your plate, and you want to top it all off with a watch glass, again, to prevent evaporation, as much evaporation as possible. Okay? You allow the solvent to run up the plate until you reach your finish line. You could allow it to go all the way to the top. That's going to be really hard, I'll be honest. So putting in a finish line, maybe 1 inch or so, 1.5 inches from the top of the plate is fine. You do want a couple of inches, though, for your experiment to spread out, to allow these chemical spots to spread out. Once you've reached the finish line, you take your plate out, you allow the solvent to evaporate, and then you'll again look at it under UV light. So, what should we expect to see? I'm not sure. I'm not going to show you exactly how far the chemicals would go, but one way they might look is if your salicylic acid, this was, remember, your salicylic acid on the first spot, it will now have moved up the plate some distance, as will your pure store-bought aspirin. And so you see they will have moved different distances. Okay? So this means they behaved differently, and that's a property that we can use, we could take advantage of to distinguish between our experimentally made samples. What we would hope, let me jump over to our recrystallized sample last. I would hope that your recrystallized sample matches the pure aspirin sample. Anything that matches means they are the same chemical. All right, so we can, just like with melting points and melting points matching, when two chemicals travel the same distance, if we've constructed our solvent mixture correctly, it means that they are the same. So it verifies the identity. Okay. Now your raw sample, this is the real, we're not quite sure what's going on with our raw sample. So maybe, hopefully we have some raw aspirin there, but maybe you would have some left over there. So again, because there's a match, what that would mean is that your raw, in this case, is impure. It's a mixture of both acetyl salicylic acid, or aspirin, and some leftover salicylic acid. All right? So that's if you see that match up. If you see a spot here in your recrystallized, it means your recrystallized is not completely pure either. Now don't be discouraged. I drew nice tight spots. Don't be discouraged if your spots are rather blobbish in shape. Okay? This is probably the first time that most of you are doing the experiment. So you might have a less than conclusive, comparison. But even with this, I could draw the same conclusion. It looks like there's a match for the recrystallized to the store-bought. Also, my raw has some aspirin in it, and it looks like some salicylic acid in there. So it's very likely that you might not get 4 nice tight spots on the plate after it's developed. Okay? Again, just like with the iron 3 chloride test, it might be great to take a picture of your TLC plate. Taking a picture would be a great idea, or while it's under the UV light, circling the spots, all right, so that you could draw a sketch of this as part of your formal lab report. Again, visual evidence that you could convey to your instructor to back up the claims that you will be making, right, about your sample of aspirins. Right? In the big picture, today's descriptive evidence that you're gathering is going to be used when you write your formal lab report to try to say, yes, I made aspirin, and here's the evidence that I have to support my claim that I made aspirin. Or to say, I made aspirin, but it wasn't a very pure sample, and here's why I can say that. Right? So it's evidence that you're going to use to support whatever your conclusion is about the quality of the product that you've made last week in lab. Next week in lab, we'll redo the iron 3 chloride test, but in a quantitative fashion. Rather than just looking for the purple color, we'll be able to measure the intensity of the purple color using a UV-Vis spectrometer. And that we can use to then calculate the amount of salicylic acid that might be present in our samples. So we can put some numbers on the purity of our samples next week. But today we can get a lot of great qualitative descriptive information. So I think that's it for the video today. I have pretty much dropped all the hints about the answers to the pre-lab questions throughout the video. So I hope you've caught them and that you'll have no problem completing your pre-lab questions in time for lab. I wish you good luck with the experiments, and I hope your samples turn out to have the quality that you're looking for. And I'll see you next week for Aspirin Part 3. 6,000, 7,000, 8,000, 9,000, 10,000, 11,000, 12,000.